The concept of variable quantum time allows us to understand the fundamentals of the reality that surrounds us, with absolute clarity and certainty. For centuries, human beings have confused the progress of the absolute time of the universe, with the time marked by our clocks. To understand this difference, let's start with an allegory. Far away and a long time ago, there was a baker who wanted to prevent his bread from burning in the oven. That is why he made an hourglass, and filled the top glass with the exact amount of sand, so that when it drained completely into the bottom glass, he had to take the bread out of the oven. And in this way the bread always came out just right. Leaving the bread in the oven during the draining of a glass of sand worked fine. But when the sand was a little wet, it drained more slowly and the bread burned. Then he established the rule of leaving the bread in the oven, only for half a glass on rainy days. And what conclusion did the baker draw? That time passes more slowly on rainy days. End of the allegory. Let's go back to our real world. What do our watches measure? They are said to measure the passage of time. But we must understand that they do not measure the passage of time directly. They measure the duration of equal and successive physical movements, which allow us to visualize the passage of time. Clocks count and display the number of these pattern movements. The tick-tock of the old clocks was the noise of the successive mechanical movements that occurred inside the clock. Digital watches measure exact vibrations per second, and are much more precise movements. They are surpassed by atomic clocks, which follow the same principle, but always measure the number of physical movements, however small they may be. The most important fact in the history of the clock was to find a universal standard physical movement, so that their measurements were comparable and made sense to everyone, everywhere, at all times. A full turn of our planet Earth, from noon to noon, meets those conditions. And the units of measurement of the passage of time were established. One spin is equal to a day, or divided into 24 hours, or 1,440 minutes, or 86,400 seconds. And what would the smallest unit have to be? Without a doubt, the Planck time, the shortest that can exist. One spin of Earth's sunlight is equal to 1.59 times 10 to the 48 Planck times. As absolute universal time passes, our clocks do not measure the passage of time directly. They measure the duration of equal and successive physical movements. The master move of our clocks is one Earth turn from noon to noon. And it is equivalent to 1.59 times 10 at 48 Planck times. The duration rules any move in a certain quantity of Planck times. Our watch is marking a certain amount of Planck times on each successive standard movement within the watch. It could be a mechanical movement, vibration, or any other movement. And when repetitive movements accumulate 1.85 by 10 to 43 Planck times, our clocks are calibrated to tick 1 second. And how are the laws of relativity explained? We already know that our clocks mark fewer seconds when they move, and when they are in a gravitational field. In other words, when our watches have wet sand, they mark fewer seconds. And we don't have to repeat the baker's mistake. Obviously, universal time does not slow down. We must not confuse the advance of absolute universal times with the slower movements that mark our watches in different conditions of the system that contains them. Let's see the progress of the universal time, both in the vacuum space and in a gravitational field. This moment is now, and everything that exists in the universe exists now, everywhere simultaneously. How long is this moment? It is instantaneous, has no duration. And this instantaneous present continues to advance the same, everywhere, so that everything in the universe continues to exist simultaneously. What's moving forward? Now is moving forward. The instant present is a property of the universe. Time is a human invention, to measure the progress of now. Like temperature and heat. Time and now are not the same. Remember the baker's mistake. The advance of now must be equal and simultaneous throughout the universe. Let's put our clock in the vacuum space, where will be a quantum time q0, which is the minimal advance of now to allow the move of a Planck length. It is equivalent to a Planck time, marked on our local clock. No movement is allowed until a Planck time has elapsed in our clock. If n is equal to 1.85 times 10 to the 43rd, then nq0 will be t0 second, marked by our clock. If we bring another clock like it, it will also mark t0. We now move this second clock, as it is calibrated, to the gravitational field, where the quantum time Q of the clock consumes more now. What does it mean? The Planck time is longer in the gravitational field, and all physical motions will be slower than in the vacuum space. The ticking of mechanical clocks will be slower. The vibrations of electronic watches will be slower. But the repetitive Planck time marked by the local clock is calibrated to 5.39 times 10 to minus 44 seconds. If n is equal to 1.85 times 10 to 43. When passing n times q Planck times, the clock was built to mark the time t, equal to 1 second. But the second from above is not the same as the second from below. We will call t0 the reference second, and t the own second of any other place in space. When we are in a gravitational field, the own quantum q will be larger than the reference quantum q0 in vacuum space. Therefore, when the clock in the gravitational field marks t equal to 1 second, at the same moment now, the clock in the vacuum will be marking more than 1 second. And t0 is greater than t. But despite the difference between the own second and the reference second, the universal advance of now is equal and simultaneous everywhere. Although the clocks mark different amounts of successive movements t0 and t, a lapse of the universal advance of the now is the same everywhere, in the vacuum, as in the gravitational field. Therefore, a portion of delta now is the same throughout the universe, and will be equal to t0 times nq0 of reference. It is also equal to the own time t times nq. Therefore, t0 times q0 is equal to t times q, which is the law of quantum time. With our satellites and spacecraft, it has already been amply verified that the relationship of the reference time marked t0 by the clock on Earth, with own time t and an equal clock in space, complies with the Schwarzschild formulas. But if we want to know in our time t0 of reference on Earth, how long the explosion of a very distant star lasts, from when it starts until it goes out, we cannot apply the Schwarzschild formulas, neither we can send our clocks to that place to measure the own time t. But we receive the photons that illuminate that explosion. We can use them as information messengers. What do we know about photons? Michelson and Morley's experiment in 1887 was the first test against the theory of the motion of the Earth with respect to the ether in its orbit around the Sun. Since then, we know that a moving body always emits photons at the same speed of light, in all directions. In 1929, Hubble adopted the Doppler effect to explain the receding speed of relatively nearby nebulae. For most of the 20th century, we have considered that a moving light-emitting body flattens the photon waves forward, increasing their frequency toward the blue, and stretches the waves backward, reducing their frequency with the redshift. But in the 1990s, with 1A supernovae as standard candles, beyond a certain distance, they would be receding faster than the speed of light. Therefore, in 1998, the accelerated expansion of space was adopted, which lengthens the wave of photons producing a redshift in all directions. Let's go back to the year 1905. Einstein published his photoelectric effect. Among other things, he verified that there is an instantaneous interaction between the electron and the photon. Therefore, when the photon is emitted, it begins to travel instantly at the speed of light in all directions. Within the photon that travels at the speed of light, the Planck time is never fulfilled. Until the photon stops when it reaches the depths of our eyes or the plate of our telescopes. Therefore, any moving body will emit the photons instantly at the speed of light, and with the same emitted frequency in all directions, which cannot change during the entire trip. And how do we then explain the redshift when we receive it? In the photon the quantum QF is continuous, it is never fulfilled. Therefore nothing can move since it is emitted, nothing can change while traveling at the speed of light. In the outer space surrounding the photon, there are Q-own quanta, which allow the photon to move 1 Planck length each Planck time. And it is received where there is an outer quantum of time Q0. The photon is emitted instantaneously, with a range of frequencies, which lasts from a universal moment now 1, until now 2. This portion of delta now, contains an emitted number of cycles, and this amount will be frozen inside the photon, until the moment it is received. But it is emitted with its own time quantum q. If n is equal to 1.85 times 10 to the 43rd, nq will be an own second where a certain number of cycles will be contained. which will be the frequency emitted, cycles per second. And we have said that it will be received unchanged, but with a smaller reference quantum q0. Therefore, nq0 is our reference second, and will contain a lower number of cycles per second, which will be the received frequency. And the frequency emitted over the received is proportional to the quanta q over q0, which is the measured redshift. And if we remember the law of quantum time, q over q0 is equal to the reference time over the own time, which allows us to add t0 over t to the redshift. Therefore, by measuring the redshift experimentally, we can know the own quantum q, compared to our local reference quantum q0. And the time that our clock would mark in that place in the universe, t, is equal to the reference time t0 that we measure, divided by the redshift of the photons received. And we have the Photon Law, which tells us that the own time of each place in the universe is equal to our reference time, divided by the redshift of the photons that it sends us. But let's now deepen the concept of time variation in our clocks. Special relativity tells us that the time t of a moving clock is equal to the time t0 when it is standing still, times the square root of 1 minus the speed of the clock squared, over the speed of light squared. Since 1905, this simple Albert Einstein equation has been well proven. If we take into account the law of quantum time, t over t0 equals q0 over q. And we have the other way of the formula of the law of quantum time, to calculate the own q in the moving clock. It means how much the speed expands to the Planck time. Let's explain now the old twin brothers paradox. One of them decided to make a round trip to Alpha Centauri, distant 4.3 light-years away, at a speed of 99.9% of the speed of light. We take both the law of special relativity and the law of quantum time. The value of the inverse of the square root, also called the Lorentz factor, is 22.6. It means that the own quantum time q in the spacecraft consumes 22.6 times more now advanced than the reference quantum time q0 on Earth. When the traveling twin returned, he had spent 113 months on Earth. That is, 9 years and 5 months. But on the spacecraft only 5 months. 9 years less than on Earth. For more than a century they were searching unsuccessfully for a simple and understandable explanation for this phenomenon. At the departure, they were together, in the same place at the same time. We can call it the moment now one. On the arrival of the spacecraft, they were together again. They shared the same moment. We can call it the moment now two. From the instant of the departure now one, to the instant of the arrival now two, they advanced the same delta now. The twins had to share every moment, every instant of their existence, during the entire journey. For the twin on Earth, its delta now was t0 times nq0. Being n, the number of Planck times contained in 1 month. 1 reference month on Earth. From departure to arrival his reference time was 113 months. Or 9 years and 5 months. For the twin on the spacecraft, its delta now was t times n on q, which is the months in the spacecraft. From departure to arrival, his time was 5 months. For the twin on Earth, t0 was 113, and q0 was 1 reference month. The total time measured is 113 months on Earth. For the twin in the spacecraft, t was 5, and own q was 22.6 times longer than 1 month on Earth. The total time measured was also 113 reference months on Earth. But only 5 own months in the spacecraft. They shared the now throughout the trip because the twin on Earth lived a more prolonged time t0. And the traveling twin lived with his shorter own time t, without realizing that he was in slow motion compared to his brother. Now let's see what happens with time around a massive body. At a great distance from the center, the market time for our clock is t0. This is the original Einstein equation for the special relativity. And Schwarzschild's great insight was to use the same equation, where he replaced the speed v of the moving clock with the escape velocity ve, to correctly explain general relativity, which allows us to graph the evolution of proper time, at each distance r from the center of gravity of the mass. And with the formula of the escape velocity, we have the evolution of t expressed by the mass. And with the formula of the Schwarzschild radius of the black hole, the proper time t at distances r is determined with rs, Schwarzschild radius. All these equations were verified with 2 equal clocks, in the gravitational field of the Earth and with ships and satellites at different speeds and at different heights. And now we can introduce the Photon Law, T equal T0 over the redshift rho, where we can see that rho is equal to the inverse of these square roots. And we have the formula for the redshift of the photons emitted in a gravitational field expressed with the escape velocity, with the mass m, or with the Schwarzschild radius rs. The redshift rho is equal to the proper quantum q over the reference quantum q0. And we can have the variation of the Planck time q in the gravitational field, which expresses how the Planck time expands as we approach the center of mass. Yes. Mass expands Planck time. The speed of light c0 in a vacuum space is a Planck length over the Planck time q0 in the vacuum space. The speed of light c, in the gravitational field, is a Planck length over the own Planck time q. Therefore, the speed of light in the gravitational field c, over the speed of light c0 in a vacuum space, is equal to q0 over q. From which we get the value of the speed of light c in a gravitational field, caused by a mass m at a distance r from its center of mass. And with this new formula, we can plot the decrease in the speed of light in a gravitational field as the distance r decreases, which was proven by Shapiro in 1964. The law of quantum time and the Photon Law allow us to see the universe from a new perspective. Time is a human invention and not a property of the universe. Clocks measure successive movements, referring to the rotation of the Earth, and depend on their own Planck time. Let's look at the cosmic microwave background. We can look again at the history of all the observations we have already made in our observable universe, but with the quantum time already explained. We accumulated a century of redshift observations on photons that reach us from stars, galaxies, and supernovae at different distances. Between the Earth and the cosmic microwave background, we have established a distance of 13.8 billion light-years. And there is also a progressive redshift, very similar to that we have analyzed in the gravitational fields. With the light of standard candles, their distances to the Earth have been measured. At first, Cepheid variables were used for relatively short distances. In 1929, Edwin Hubble determined a linear variation of redshift with distance. He interpreted it as a Doppler effect, where the dimensionless number z is equal to the speed of the emitting body over the speed of light. And the redshift is z plus 1, as plotted here as rho. Therefore, according to Hubble's law, galaxies move away from us at a speed v, proportional to their distance d, creating a constant h0, the Hubble constant, whose final value has been discussed ever since. But in the 1990s, supernovae 1a were used as much more luminous standard candles, and some of them could already be observed very close to the cosmic microwave background, where the redshifts of the received photons were very high. The concept of the Doppler effect had to be abandoned because these supernovae would be moving away at several times the speed of light. For this reason, in 1998 the phenomenon of accelerated expansion of space was adopted to explain these superspeeds of receding. While the accelerated expansion of space explains the redshift, it would take an enormous amount of dark energy to scatter everything that exists in the universe, even pushing the cosmic microwave background away, to a current distance of more than 46 billion light-years from the Earth. Either we accept the dark energy explanation, which is nowhere to be found, or we apply the photon law to that universal redshift, so our clocks would slow down, as they get closer to the cosmic microwave background. According to the latest measurements published by the Planck collaboration in 2018, a value of z equal to 1089.8 corresponds to the microwave background radiation. This corresponds to a redshift z plus 1 of almost 1100 in the cosmic microwave background. That means his own q Planck time was 1100 times our actual q0 Planck time here on Earth. And the speed of the first emitted photon was 273 km per own second. Therefore, that first photon in its first proper second only traveled 273 kilometers, because we have a universal Shapiro effect. But so far, we have considered that the cosmic microwave background photons have always traveled at 300,000 kilometers per second, since the first second. That is why we say that the radius of our observable universe is 13.8 billion light-years, or 13.04 by 10 to 25 meters. But in a first rough calculation, with the Shapiro effect of speeds of light, the distance traveled by photons from the cosmic microwave background is only 8.26 times 10 to 25 meters. In other words, The radius of our observable universe is only 63% of what we have calculated with the constant speed of light. But it can also be argued that the brightness of standard candles is proportional to how many kilometers they are away from us, regardless of whether those photons traveled faster or slower. In that case, the cosmic microwave background would actually be 13.04 by 10 to 25 meters from us. But then the age of the universe would be about 22 billion years, of the time of our clocks, which would be how long it took those photons to reach us. And now, we start a very interesting part, because if all these deductions are correct, then the consequences are enormous. Let's look at an imaginary example first. In a place of the universe, we have the surface of a large massive body, where its gravitational field manifests up to a certain height. And I observe it from outside its influence, where I have a clock to measure my time of reference t0. On the surface of that massive body, I observe a distance of 10 kilometers, where a car moves at a constant speed. And when it moves from 0 to 10 kilometers, I have measured a time t0 equal to 1 hour of my reference clock. Therefore, I observe a speed of 10 kilometers per hour. So I receive a photon from that line. And I measure a redshift equal to 6. According to the law of quantum time, the proper time of this displacement will be equal to 60 minutes of the reference time, divided by the redshift, which is 6, equals to 10 own minutes. Therefore, the car's own speed will be 60 kilometers per hour. Imagine now that I'm looking at two cars at the same time on this same surface. They are about to collide head-on, and I see them approaching at 10 kilometers per hour. But I see a big accident in slow motion, which is neither logical nor normal. Therefore it is not what I saw. My observed speed of 10 kilometers per hour is an error. We need a name for this phenomenon. We can call it the Time Mirage. The clash in one's own time is what happens, because all the physical laws are fulfilled in the own time of each place. We can constantly verify that the physical laws here on Earth are fulfilled with the times of our own clocks. Regardless of whether someone is observing us with a super spyglass, from a great distance, somewhere in the universe. Physical laws are all accomplished with the own time in each place of the universe. But now let's see a more real example. In the rotating center of our Milky Way, there is a very massive black hole. A star rotates around it at a very close distance, and therefore very submerged in the gravitational field of that black hole. Far away, almost at the edge of the galaxy, is our Earth rotating around the Sun. In this place, the gravitational field of this black hole is very weak. On Earth, there is an astronomer, using a reference clock with a very large unit of time, which is equal to the number of n Planck times that add up to 1 year. The astronomer observes the rotation of a complete orbit of that star, which lasts 40 years. Therefore, its reference time t0 is equal to 40 years. The light from that star sends us photons, and the astronomer measures a redshift equal to 20. As we have seen, n quantum q is equal to the redshift times n reference quantum q0. Therefore, nq is equal to 20 terrestrial years, because its Planck time consumes 20 times more universal now than on Earth. And now we can apply the Photon Law, where the star's own time t is equal to the reference time t0 on Earth, divided by the redshift. In this case, 40 Earth years are divided by the redshift, which is 20. Therefore, t is equal to 2 Earth years, which is the duration of a rotation of the star, complying in proper time with the law of universal gravity. The astronomer publishes his observations in a graph of the orbital velocity on the y-axis and at different distances from the black hole on the x-axis. First, the Earth is located, and then the star observed at a very short distance from the black hole, which, as we have seen, rotates in 2 years through a complete orbit. But the astronomer observed it with a redshift equal to 20. And in his own time he had to wait 40 years to see, in slow motion, a complete turn of that star. This is own time the star rotates. But this is how we see it as a consequence of the mirage of time. And next, a second star is observed a little further away, where the same deviations are observed, but more attenuated. And the third star with minor differences. And a fourth. And so on until it reaches the solar system. All the stars in the galaxy rotate in their own time, following the blue line, and complying with the law of universal gravitation. And on the red line, where the same stars are located, but rotating as we see them, according to our mirage of time. And what do our astronomers publish? These are the observed results accumulated up to now because that's how we see it. According to our mirage of time. But that's how they rotate in their own time, complying with the law of universal gravitation, just like the planets that rotate around our sun. Due to the mirage of time, to explain these very slow spins near the black hole, our astronomers ask for the existence of a mysterious dark matter, which no one has found so far because it does not exist. We don't need black matter. And if we look at a galaxy from the outside, in the very bright center are all the stars closest to the black hole, at its center of rotation. Being very submerged in the gravitational field, the redshift of their photons is very high, and the apparent speed of rotation that we see is very slow. But with the Photon Law, we can correct what we see. With the own time of those stars, they comply with the law of universal gravitation, which confirms that we do not need dark matter. In summarizing, in the first analysis with quantum time explained, we have important consequences, which will bring great changes in everything we thought exists in our universe. We can eliminate dark energy. And also dark matter, because there is only ordinary matter. 100% are mostly neutrons, protons, gluons, electrons, photons, and some other quantum particles, plus all the real energy. These verifications magnify the importance of these two laws, so as not to continue making the baker's mistake, by confusing the time of our clocks with the advance of the universal moment. There are more conclusions thanks to the variable quantum times. That's what the next videos from this channel will be about. If you subscribe you will find out when they are published. See you soon and thank you very much for your own time.